name is Aditya Singh.
My name is Devan Mehta.
And we are ECE students at UT Austin.
And this is our energy optimization system project. Phantom energy is energy consumed by a device when it's not in use, and usually consumes up to 2/3 of a device's daily energy usage. Current solutions to this problem are not optimal, nor are they cost effective to be considered viable solutions.
Our project provides the means for users to wirelessly control power going to and from their devices and monitor how much energy and money they are saving, all in one very cheap and accessible solution.
So this is the PCB that we designed for this project. It includes a slot for our ESP32, a relay block, and an L293D. So here's the PCB and the PZEM004T with our load device. The load device has a hot and neutral wire. We monitor the neutral wire using the PZEM clamp, and the PZEM translates the readings into numbers that ESP32 can read through the use of UART with Modbus RTU protocol. So we also had a blue status LED, which tells us if Wi-Fi is connected or not, and then just UART status LEDs over here on the PZEM.
The ESP32 will then communicate live readings to the locally hosted website built through its built-in Wi-Fi feature. Additionally, the ESP32 will control the state of the relay with the GPIO through the L293D. The relay could cause inductive currents, and it carries large voltages from the wall that could damage the microcontroller, which is why it is necessary to use a middleman like the L293D. For more information regarding specificities of components, wiring diagrams, or PCB designs, refer to the README.
To get live readings and control of our system, we made a web app hosted on the ESP32. Read the web app server part of the README for more info. There's also a dark mode and a light mode.
We sampled the live power for a full minute to get a baseline range that our device would normally operate in. For our calibration logic, we made a frequency histogram with buckets that group together samples with 0.1 watt widths. Then ignore any buckets that don't have a minimum sample of 10 in them to eliminate outlier power samples. This is where you enter your electricity rate, which you can find through your electricity bill or provider. For our instance, we're going to use 0.112.
So here's the dashboard view that shows the baseline range that we calibrated. We use non-volatile storage, or NVS, to save the calibrated baseline range in case our device shuts off or loses power, or etc. We also have a live activity feed that shows the past 30 events that happened, which could include when the device went to sleep, high power, if night optimization was turned on or off, or if the load was manually turned on or off. To prevent random spikes or anomalies in power from changing our status to high power or sleep, which could also trigger the relay if night optimization is on, and more on that later, we added a 4-second debounce.
So this is how our night optimization actually happens. Assuming a device has been on for at least 15 seconds, when it's nighttime, between 12 to 8 a.m., and our device falls into sleep mode, we cut the power to it using the relay to save energy.
So we also built a live cost estimator that uses the average daytime power and previous night optimization history to calculate savings in whatever time frame you prefer. More on how we calculated in the cost estimator model section of the README. The model's accuracy increases as more nights go by. Of course, right now, there have been no nights that the night optimization logic has happened, so our accuracy is low, and it doesn't show any savings. But you can see the actual results in the web dashboard as well as the performance section of the README.
Through our testing, our product hasn't reported any failures or premature shutdowns. It could last consumers years without failure, even including features for when the Wi-Fi cuts out. We have detected 0 false relay activations, and it scored a perfect 20 out of 20 on our alerts testing.
Our product can save up to 84% of power during sleep optimization phase, amounting to about 4 cents a month. Keep in mind that our device/load for testing purposes operated at a very small wattage, which was about 1.6 watts. So bigger appliances or bigger loads will amount to much bigger and more impactful savings.
Future improvements we could make include utilizing the other terminals on the L293D or switching to even more terminals on the ULN 2003A. This would expand the number of devices we can connect and control through our app.
And additionally, we could allow the user to decide a custom sleep optimization window that would better fit their schedule rather than just having it to be 12 a.m. to 8 a.m.
Thanks for watching.